In this video we're going to be covering this integral here, which is I of a, which equals the integral from 0 to pi over 2 of sine to the power of a of x dx, where a is a positive real number. Now, just so everyone is aware, we can actually extend this into complex numbers, but for this video I'm only dealing with real numbers, and again where the parameter a in this case is greater than or equal to 0. Okay, so the way in which I'm going to tackle this function is to employ the beta function, because the beta function has a representation of this function that is very, very similar. In fact, it's identical, and so what we need to do is take this form and put it into the form of the beta function, which we will then extend into the gamma function. So firstly, the definition of the beta function, x comma y, this is the standard definition, is equal to the integral from 0 to 1 of t to the x minus 1 times by 1 minus t to the y minus 1 dt, and this holds for all positive values x and y, I believe, or is it x and y greater than 1? We'll probably have to check. In fact, why don't we just check really quickly now. So let's go to beta function. Okay, so we see the definition here. And we see that this is for the real part of x, so for any complex numbers x and y, for the real part of x is greater than 0, real part of y is greater than 0. Here we're dealing with just real numbers, so for us it will be x greater than 0 and y is greater than 0, which we've got satisfied. Okay, great. So another representation for the beta function is this representation that we have here. And in order to get this representation, we just make a very simple transformation. We just let t equal either cos squared of x or sine squared of x, and with some very simple algebra, we're able to show that it's equal to this integral. Now, you'll see here that the integral that we have here is very, very similar, if not, sorry, when I say similar, it's identical to the form that we have within here. The only major difference is that we've got the 2 out the front of here, whereas we don't have anything out the front. Obviously, this is a simple thing to be able to overcome. What we need to do is just divide this 2 onto this side here, and you'll see that that's what we've done here. So if I want to have just this integral component, which we have here, that's just equal to 1/2 of the beta function. Okay, so now let's have a look at our integral and show that it can actually be positioned into this exact form which we have here, which is, as we went through just then, the beta function. Well, the integral from 0 to pi over 2 of sine to the power of a of x is the same as the integral from 0 to pi over 2 of sine to the power of a of x multiplied by 1, and 1 is just equal to cos to the power of 0 of x. So we see here, the reason why I've done this is because, again, I want to put it into this form. So now what I need to do is I need to solve for the values of x and y, which produce a and 0 respectively. This is obviously just some very simple algebra, and that's what we're going to do in the next step. So for the first one, we want to solve 2x minus 1 is equal to a, which is what we have here. And with some very simple algebra, we see that x is equal to a plus 1 over 2. Similarly, we want to solve 2y minus 1 is equal to 0, which is what we have here, and we can see with some simple algebra that y is just equal to 1/2. And so our integral, which is the integral, again, from 0 to pi over 2 of sine to the a of x dx, is equal to 1/2. Remember, we had to divide that 1/2 out the front. Beta, we've replaced now x with its value, a plus 1 over 2, and y with its value, 1/2. And you'll see here, in this case, these both satisfy the conditions upon which we needed for the beta function in order for it to be convergent, which is x and y is greater than 0. So if we wanted to just represent the integral in terms of the beta function, what we've got here is the solution. We could extend it probably a little bit further, but in general what you see in practice is that the beta function representations are often, if not always, converted into a gamma function representation. And that's because there is a defined relationship between the two, and it's just easier, I think, in most cases, or better for a number of mathematicians or mathematical work in general, to be able to just have to deal with one function over two functions. So the relationship between the beta function and the gamma function, which is what we have here, if you go to that Wikipedia page, you'll see that there is actually a proof for this. By the way, if people would actually like to see a video of the proof of this actual relationship, please let me know in the comments and I'll be happy to put together a video. But what we have is that the beta of x comma y is equal to gamma of x times by gamma of y over gamma of x plus y. So therefore, our integral, which we've got, is 1/2 of beta of a plus 1 over 2, comma 1 over 2, is equal to 1/2, so that's just this 1/2 component here, and we've got gamma of x, gamma of y, over gamma of x plus y. So that becomes x, remember, in this case is a plus 1 over 2, y is 1/2, so we have gamma of a plus 1 over 2, gamma of a half, over gamma of x plus y, which is gamma of a plus 1 over 2 plus 1 over 2. And so, simplifying that out, we firstly note that gamma of 1/2, this is probably, without a doubt, the most famous known gamma value outside of the integers, and that is gamma of 1/2 is equal to the square root of pi. Again, if people would like to see a proof of that, or a video explaining that, please advise within the comments and I'll be happy to put together a video. So this here, this gamma of 1/2 gets replaced with the square root of pi. This over 2 is just this component here, the 1/2 that we had before. And then we just have the remaining components, which is this component and this component, which is, whoops, sorry, I don't know what I'm doing there, which is equal to gamma of a plus 1 over 2 over gamma, you'll see here I've just put it over a common denominator, a plus 1 over 2 plus 1 over 2 is the same as a plus 1 over 2, which is a plus 2 over 2. And so now, instead of representing this integral in terms of the beta function, we've now got it represented in terms of the gamma function. Both are equivalent, obviously, and it really depends upon the individual application as to what you would choose. I've decided to reduce it down to the gamma because that is the general convention. Okay, so now just as a short summary, we now know that the integral of I of a, which is the integral from 0 to pi over 2 of sine to the a of x, is equal to square root pi over 2 gamma of a plus 1 over 2 over gamma of a plus 2 over 2. Now, one of the beautiful aspects of the beta function is that it's symmetric, and that means that beta of x comma y, or maybe over here, x comma y, is equal to y comma of x. So if I swap these around, it gives the exact same value. And so I'm going to leave a little task for the viewer here, or the reader as it's often referred to in a textbook, to show that the integral that we just dealt with, which is with the integram which is sine of a of x, is actually equivalent to when we have the integrand is changed to cos of a, cos to the power of a of x, and that equals the result, as I said, as we had before, square root pi over 2, gamma of a plus 1 over 2 over gamma of a plus 2 over 2. Okay, great. Well, I hope you've enjoyed this video. If you have, could you please give it a like? If you like these sorts of tutorials and you'd like to see some more, please hit subscribe. As I say in all of my videos, I take requests. So if you have a request for a family of integrals, this is sort of a family of integrals that we're dealing with here that you would like to have covered, or maybe just a definite or an indefinite integral that is specified for a given set of parameters, please either comment or send me a message, and if I'm able to actually solve it myself, I will happily put together a video. Well, if I have time, I'll happily put together a video and upload it. Otherwise, have a great day. Bye.